right, hello everybody. So sorry I can't be there today. I know it's not probably the best time because we already lost a day with snow, but that's how it works out sometimes. You guys know how that goes. And so today our focus is going to be on finishing the notes. You guys are going to have 3 separate homework assignments to catch you up because again, we kind of lost a day. And when we come back on Friday, we'll address the homework. We'll be trying to put all these ideas together. So it's important that 1, you finish the notes, 2, you finish the homework to the best of your ability, of course. So like you're not lost on Friday when these ideas start to get applied. All right, so let's get to the show here. So just as a quick review, because it has been about a week since we've been in class, you guys did this big investigation, which you actually did all the things we're about to talk about. We had a chance to kind of talk about it, break it down, and now we're just trying to do some organization. So as a reminder, this is a big, like gigantic double wide piece of paper. The sub has, extras if you need it. Right, so we should start out by probably reviewing what we did last time. We talked about shapes being mathematically similar, which has a eerily similar definition to things being mathematically congruent. If they're similar, they're what we're going to call proportional. And proportionality simply just means 2 things. So this word proportional by itself does equate to the idea of similarity. They're not synonyms, but they're closely related. If you call things proportional, that means you're agreeing that all corresponding angles have to be congruent, and then all corresponding sides have equivalent ratios, which means essentially they have the same scale factor or K factor. Okay, so we're not looking at congruency necessarily. We're saying like if I take these sides and multiply it by a number, I get these new sides. But that K factor, scale factor, as we saw, shows up in lots of different ways. We took these notes last time, and it's a really important thing that we never kind of forget or lose sight of as the work gets more complicated. But we have the similarity proof we have to take care of. In other words, we have an initial condition that we always have to check, which means nothing really matters unless we know they're similar in the first place. In the review of these notes, you can notice that the best way to prove things are similar, the easiest way, and frankly the most common way, is to prove that you have 2 angles that are corresponding and congruent in your triangles. And these were the examples from last time. And you'll see that I'll try to trick you in different ways. Like one, I'll like reorient the triangle so they're spinning. Maybe I won't give you all the angle values. Maybe I'll set you up so you have to recognize vertical angles, reflexive angles, corresponding angles, which means yes, it's going to be proof coming very, very soon. But in the end, if you're going to prove things are congruent, that means you know they're proportional. If they're proportional, it means we get to apply it. And so moving over to the right, also, these were the examples of different ways we can see that. You're welcome to go back to the video and pause that video if you need to see it. So moving over to the right, now we have to think about the application of knowing things are similar, which equates to knowing the application for proportional triangles. Now, this is, no kidding, the most important thing you can know. If you know triangles are similar, that means we can solve proportionality. Oops, let me change my pen there. We can solve proportional triangles. Okay. Now, the reason why this is the most important thing is because this is the most common setup that you'll see out in the world, so to speak. Proportional triangles, and that's what this poorly handwritten thing says, proportional triangles are just like a modelable scenario out there in the world. So here are 2 quick examples, again, ramping up the difficulty a little bit. Even in example 1 on the left here, we want to take a second and just acknowledge that we do actually have similarity. Okay, we have angle-angle similarity because we have an angle that matches at the A point or the A vertice with the D vertice. Then we have another point that matches at the Bravo vertice with the Echo vertice. And so we just have the similarity that we're used to seeing, so to speak. Now, in terms of how to set this up, we have to remember that proportionality means that we have 2 ratios that are congruent. Now, the ratios in this case are just a comparison of 2 items, which means I'm going to compare 2 items and then set them equal to another 2 items, all that should have a relationship. You should note that in terms of similar triangles, they have to make sense 2 different ways, horizontally and vertically, and I'm going to show you what I mean. So take this first set of triangles. We see a 5 and a 15, a 3 and a Y. It literally does not matter where we start. I'm just going to pick the 3 here as our starting point. And so if I start my ratio with 3, I have to compare 3 to something, and I do have choices. I could compare it to the Y, and the relationship would be in the same triangle, or I could compare it with the 5, and the comparative relationship will be corresponding parts. This is far more common to think about them in terms of corresponding parts, which establishes my first ratio 3 to 5. Okay. Now, I have to match that ratio perfectly. That's the nature of proportionality. I set a ratio and then I try to match it. Okay. And given all my choices, I think I have to start with a y. Now, the reason I'm starting with a y is because it gives me a horizontal relationship with the 3. The 3 is from the small triangle, therefore the top of the next ratio should also be from the small triangle. And then I should pair that with 15, and that would give me what I call a two-way match. Now, just for clarity, what I mean by two-way match is that if I look at my proportionality this way, there's a match because 3 and y come from the same triangle in the same way 5 and 15 do. Okay, I have a vertical match because 3 and 5 are corresponding parts in the same way y and 15 are corresponding parts. And so if you have like this two-way match, horizontal and vertical, and everything's aligned, then you know that your proportion is valid and therefore is solvable. Okay, going back to like this setup, I had 3 over 5 is equal to y over 15. The only thing that could not have gone here, okay, would have been 15, because that would not have given me any kind of matching horizontally or vertically. 3 wouldn't match with 15 because they're not corresponding parts, and then 15 and 3 wouldn't match because they're then in the opposite order as 3 to 5. Okay. Now, having said this, we can now solve it, and we can talk about variance afterwards. Now, in terms of solving, I'm not concerned with the methodology you choose. Most people have kind of fallen to like using this cross multiplication reduction method. I think that's perfectly fine. Shows much work is needed here. I have 5y is equal to 45, and so let's see, y is equal to 9. Okay. Now, before we move on and talk about other variants, we should definitely check our work to make sure that we're correct. Remember, proportionality means that we have equivalent ratios, and so we should check the ratio value per side. What I mean is we should check 3 divided by 5, and if you grab a calculator and check with me, I get 0.6. 0.6, there we go. And we should check that against y over 15, which is 9 over 15, and we can see that we also get 0.6. That's the nature of proportionality. We're choosing a number to match ratios on either side of an equal sign. That's it. And so y is equal to 9. Now, I said it has to make sense 2 different ways, and so there were other ways to write this proportion. For example, if we start with 3 again, I could have matched that with, let's see, I could have matched that with y. And so my vertical alignment is now that they're from the same triangle. And of course, I would match with 5 and 15 because the vertical alignment is from the same triangle. Okay, so we have a vertical alignment that comes from same triangle. If I look at 3 and 5 and y and 15, those make sense because those are corresponding parts. And so again, ratios are not fractions, so the order is a little bit more loose, but the point is you can kind of write these different ways. If you solve this one I just wrote, you'll also get y is equal to 9, and that makes it equally valid. Okay, and there are other variants, but those are the two I want to cover now. If you move on to this thing on the right, or the example on the right, again, the first thing we should do is probably acknowledge that we do have similarity, even though it's not part of the assigned problem. If we notice that we have vertical angle theorem here in the middle plus our given angle, we do accomplish similarity, which allows us to write this proportion. Side note, if you're wondering if I'll give you a set of triangles, say, hey, set up and solve a proportion, but they're not actually similar, and so the point of that question was for you guys to notice it wasn't similar, yes, I will totally do that. So you always want to at least kind of put a second into thinking, are these even similar? Okay, now having said that, we have to set up our proportion. Okay, proportion again is going to be a ratio. It's the same as a ratio. Okay, and again, how we start this is completely up to us. And so I'm just going to pick like this 12 right here and start a ratio. And I have to pick a part that matches with 12. Given that 12 is located between the blue angle and the no angle, I can look at the little triangle between the blue angle and the no angle, and I get a 6. 12 is part of the large triangle, so what goes right here should also be part of the large triangle, and that's going to be my 6 here. Okay, and that is located between the red angle and the no angle. Therefore, between the red angle and the no angle, I should find my component, which is z. Okay, let's try. There we go. That's a little better. That's my z. Now, once you get to the proportion, again, how you solve it's up to you. I can cross multiply. That's certainly fine. I can also notice if I take the top times 2, I get the bottom times 2, I get the top. And so since it has to match the same ratio on the right as this times 2 vertical scalar, I know that z has to equal 3. Okay. I should check my ratios, even though this one's going to be fairly easy. 12 over 6 has a ratio value of 2. 6 divided by my z value of 3 also has a value of 2. And so I know that I'm correct. And yes, you should always check that. That's just part of good mathematicking. Okay. Moving on to the examples on the back. Again, we're going to see different levels of trickery. So right off the bat, I can notice my first examples do actually have similarity. I see 2 given angles and 2 given angles. And so it's just a matter of writing my proportion. And so I start with this P. I can match with a 7. I can notice that the 7 and the P are both trapped between the 1 marked angle and the 2 marked angle. In other words, they're corresponding. Okay. And then 16 is in between the angle marked with 1 arc and the angle marked with no arcs. And so that should match with 8. So that'd be 16 over 8. Again, how you choose to do this, cross-multiplying, scaling, however you choose to do it is up to you. Either way, you should get the p-value, though, to be 14. Again, checking our ratios, 16 divided by 8 is 2. 14 divided by 7 is 2. So that ratios check out. Moving on to example 2. We have our vertical angle set in the middle, which is familiar. We have these parallel lines cut by transversals, so I can use alternate interior angles. The thing about the angles and why I'm suggesting this, the angles can actually help you locate corresponding parts. And so sometimes this is the best strategy, especially if the diagram gets complicated. Having said that, if I take a look at, I don't care about my battery. If I take a look at this length, okay, is marked between the 1 angle and the no angle, and so that's going to give me a 24. Okay, and so on the other triangle, I'm looking between the 1 marked angle and the no marked angle, and that's going to give me a 12. And so I'm just using my angles to kind of help me locate stuff. 24 is part of the large triangle, so I'll start in the large triangle again. Ooh, meant to be a different color, but that's okay. There we go. And so the P side is locked between the angle marked with 1 arc and the angle marked with 2 arcs. And so my small triangle, I'm looking for the same length. And so that should give me P over 10. Okay? So again, we have vertical alignment, horizontal alignment. This P value is going to be 20. All right. Here again, we're seeing like a twisting, a reorientation, trying to get confusing, but we see 2 angles in each, and that can go a long way to helping us. If I look at the location of A, it's between the right angle and the angle marked with 1 arc. And so that has to match with 16. So I'll go 16 over A. 16 is part of the small triangle, and so it's just to start with 10, also part of the small triangle for a horizontal alignment, and that matches with 15. All right, so cross multiplying, let's see, 16 times 15 is 240, so that'd be 240 is equal to 10A, and so A in this case has to equal 24. Okay. Lastly, this is the example I would say is probably the trickiest example. Allow me to zoom in a little bit here. Let's go, 200? There we go. Now, the reason this is tricky, maybe you're not going to be tricked by that, but it's okay if you are. If you look at this guy right here, that's definitely a reflexive angle. And then we have parallel lines, so we have corresponding angles. So we know similarity applies. But what's important here is that we see both triangles. If you were to try this on your own, in fact, you probably want to pause and just try it, then come back to this part. If you got this question wrong, you likely set up something like this. So 10 over 14 is the same as 15 is to x. If you solve this out, you will get the wrong answer because this proportion itself is actually wrong. Not that you did the algebra wrong, but the proportion is wrong. The reason why this is wrong is because you may not have noticed the orientation of 2 triangles. And so we definitely have the small triangle. The second triangle in question is this large overlapping one. Okay, now to realize why this proportion is wrong, let's pull the triangles apart and relabel them. The small triangle is easy. So we know we have 10 on the side and we have 14 along the bottom. We know x goes here along the bottom of the large triangle, but the side triangle is not 15, which is why this value is actually wrong. So 15 goes from here to about right there. 15 only covers part of the triangle itself. It only goes to here, essentially. But you need the entire side of this triangle, which is actually 25. In other words, you have to do an addition problem. This is probably by far the most common mistake made in this work. So like the actual ratio you're looking for, not this guy, would be like 10 is to 25, in the same way 14 is to x. Okay? So like you have to make sure you're using whole sides in your comparison. This overlapping configuration is one that you'll see pretty much forever in every level of math from here on out, because they want you to forget that overlapping triangles, you still need to make sure you're using whole sides. In terms of the solve, let's see, we have 25 times 14, divide the result by 10, and so x in this case is equal to 35. Okay. Now we can go back and double check the ratios, but given the length of the video, I'll have you guys do that on your own. Okay, and so this is the most common setup in terms of applying. Okay, so if we zip back to the notes, this is now in the bottom right quadrant of your note side. You have this thing you have to know, because like, yeah, you have angles here and you can prove things are similar, but what if you don't have angles? And so I would offer these are the notes for the second easiest way to tell figures are congruent, and that's actually just to use the other half of the definition. So recall the definition of similar triangles that you have all corresponding angles congruent, but also all corresponding sides proportional. And that's what you can actually check also separately to see if things are similar, is to check side ratios. In fact, I should actually say this is actually to check all side ratios. All right, so what I mean by that, if you look at the triangles here that are in orange, and I wanted to prove that these are similar, yes, I could check angles. I left them there to help us verify these were actually going to be similar to begin with. But what I really want to check are the sides. And so if I notice where 10 is between the 1 mark and the 2 marked angles, that compares with 20, which means I can write a ratio 10 over 20. And that's like checking like side 1. But the definition says all side ratios, so I have to make sure it matches everything else. Now 10 over 20 establishes a small triangle over big triangle ratio, and so I have to check that against 7 over 14. And then lastly, the sides between the 2 mark and 3 mark angles would be 6 over 12. Okay, now grabbing a calculator and doing this in your head, 10 over 20 gives you the ratio value of 0.5. Okay, for side 2, 7 over 14 is also going to be 0.5. And then for side 3, because we had to check all 3 sides, right? And 6 over 12 is also going to be 0.5. Okay, since all the ratios are the same, we can claim that triangle ABC is similar to triangle DEF just by checking side ratios, just the 3 sides. In other words, side, side, side. In example 2, we're going to see much the same. So if we notice where the 6 side is, that's between the right angle and the double marked angle, so that matches with 9. Okay, and so again, it doesn't really matter, remember, which way we write this. It can be written this way or in reverse. We just have to stay consistent. And so if we go small triangle to big triangle, it has to be small triangle, that's 8, to big triangle, 12. And hypotenuse small to hypotenuse large, and so 10 is to 15. Okay, now we can't claim this is similar unless all 3 sides match. Unless we have side ratios, not congruency, but ratios. And so we grab a calculator, convert this to a decimal, because that's the easiest way to compare. I have this one is going to be 0.6 repeating. 8 divided by 12 is also 0.6 repeating. And then 10 over 15 is also 0.6 repeating. Okay, so since we have equality across all 3, we can make, again, a claim on similarity. So let's say HIG, similar to triangle, so HIG, KLJ. And that's, again, going to be by just checking the side part of our proportionality statement. So this is important because if you don't have access to angles, this gives you a second way to check if things are similar. And if you know things are similar, then you can set up and solve proportional triangles, which is honestly the whole point. Okay, if you flip this over in the back, you can notice this example is the same, so we'll just skip over that. But you should try this one quickly before I reveal the answer. So like this is the part where you pause the video, set up some quick ratios, and then resume the video, double check, all right? Okay, now that hopefully you've done that and just didn't like keep playing the video, we have to set these up. Now this does present a dilemma because in the notes I actually provide you like with an order, but there's no order here, and so we have to decide which side matches to which side. There is an easy principle though, and this nickname in mathematics is the Goldilocks principle. If you remember the story of Goldilocks and the three bears, it says like a mama bear, a baby bear, and a daddy bear, and they're different sizes, and so in mathematics we use that to explain a very simple phenomenon. If we look at the right-hand triangle, the bigger of the two, 20 is the largest side. And so even though there's no angles to help orient us, we know it has to correspond with 5. The reason we know that is because if it's the smallest in one the largest in one triangle, it has to be the largest corresponding side, or has to correspond to the largest side in the other triangle. And so something that's the largest side in the right cannot correspond to something that's medium or small on the left. Likewise, if I look at the smallest side length, which is 16, that has to correspond to the smallest side length here, which is 3. And then medium, mama bear, 18 has to correspond with 4. All right, now in terms of checking this, we just have to check the ratio values to confirm they're the same. 20 over 5 is going to be, let's see, that'd be 1/4. Let's see, 20 over 5. Let me double check a math. It's going to be 4. Oh, oof. Okay, 16 divided by 3 is not 4 though. 16 divided by 3 should be some number that I can't do in my head. 16 divided by 3, what am I doing? Divided by 3, boom, there it is. 5.3 repeating, okay? Now we can stop here because the rule is all the ratio values have to be the same. We've proven 2 are not the same, and so we conclude that this is not similar. This is why it's important not to assume they're similar unless you're told explicitly you can. You should always try to confirm similarity, and there are now 2 main ways to do that. You have angle check, and now you have a side check, all right? Last section, if you go back to the notes, this is the notes. Let's talk just on the grid. There's no big secret here. You guys have actually figured all this stuff out. We're just confirming it. So the K factor applies to side length. It keeps the angles the same. And it affects distances. It affects perimeter. It affects area in a way that we're going to talk about later. But it also affects coordinate values. And if you're on a grid, coordinates really are the premier way you want to figure out how dilations happen. Now, I can ask you to do 2 basic things. On the left, I have an example of you telling me what the K factor is, essentially confirming that you actually have a dilation taking place. On the right-hand problem, we had to perform the dilation, right? So getting into like the left-hand side, the coordinates are really going to be the key here. So if you want to confirm that a dilation, in other words, similarity happens, the very first thing you should check are the corresponding vertices. Okay, now I have these kind of pre-labeled just so it's a little bit easier for me, but you probably want to like pause the video, catch up with the labeling, and then come back. Okay. Now what I mean by confirming the K factor, we know the K factor affects everything, including these vertices. So if I take any set, say like this 4, 10 and this 2, 5, I can ratio the corresponding parts to check the K factor. So here I have a 4 and a 10, here I have a 2 and a 5. And so I probably want to check them in terms of ratios. So I'm asking myself, is 2 over 4 the same thing as 5 over 10? Okay, and we can confirm that they are. They both have a decimal value of 0.5, which confirms that these have more or less been dilated. Now, keep in mind, we can mess up the order. In other words, we could have looked at this as 4 over 2 and 10 over 5. That would have given us a K factor of 2, still confirming their similarity. Now, on dilations especially, you have to be careful, and you have to ask yourself, should I be using the K factor of 0.5 or the K factor of 2? Because if you flip these ratios, you have 4 over 10, or 4 over 2, excuse me, and 10 over 5, which would give you the K factor of 2. Now, the way to check this is by looking at your vertices. Which one comes first, in other words? Is the C the value, is a blue one, the C the preimage, or is the C prime the preimage? Now, based on our work last semester, of course, the bigger object is first, so that means we're reducing in size, and the K factor of 0.5 actually applies. Now, we do need to check all of these, right? So we can't just get away with checking one, we should check them all, and let's just see if they all reduce by half. Here we have 10, 10, and half is 5, 5, it checks out. If we cut 10 in half, we get 5. If we cut 6 in half, we get 3. That works out. I didn't actually mark this one, but this is 4 comma 6, and they cut that in half, it'd be 2 comma 3. And so the first thing you have to do to check this is to check all the vertices. The second one comes directly from the investigation we did. Now, even though this is in reverse order, this is kind of coming full circle. If I connect the A and the A prime vertice and extend that line, and the B prime vertice, extend the line. C and the C prime vertice, extend the line. And then D and the D prime vertice, extend the line. We can notice that all of these converge on one central point. Okay, this point, because it's there, first of all, again confirms the dilation. And it's no secret here, this is called the center of dilation. Okay, these lines, even though we can call them the mapping lines, these are called the lines of dilation. Okay, and in short, the presence of the K factor affecting both vertices and also the lines of dilation going back to a center dilation confirms that we do indeed have a similarity on a graph or a dilation. If we turn that to a tool, we can actually perform a dilation by using the same principles. Now, unless explicitly told otherwise, it is safe to assume that your dilation is at a 0, 0 center. And so I'm drawing in my lines of dilation more or less as a guide to make sure like I'm doing this properly. But essentially all we have to do is take our K factor and multiply to each of our vertices. Now the K factor here is 1 over 4 as a fraction. That tells us one, we're reducing because it's a number less than 1. But it's probably easier to look at this as 0.25. Okay, so if we take 0.25 and multiply it to our vertice, A, we get A prime to be 0, comma 1, because 0 times 0.25 is 0, and then 1 times 0.25 is 1. Okay, and so we can map that. I'm going to change colors here. And so that means 0, 4 maps to A prime, which is right here. Okay, and that has the coordinates of 0, comma 1. Okay, I wonder if I can zoom here. That might make it easier. Not really. Okay. We'll just have to deal with it. Okay. If we go around the horn, if we take 4 comma 4 and we multiply by 0.25, we'll have B prime to be 1 comma negative 1. Okay, so 1 comma negative 1. Please notice both those points fell right on our lines of dilation, right on these red lines. That helps us that should help us get confidence. This is all going very well. So C prime times 0.25 would be negative 1 comma negative 1. And again, it's going to be right here on this line. Okay. If we connect these lines, we should get our image triangle. And we should notice two things. One, they all fell on these red lines. And two, we do have perpendicularity between these. Between our side lengths, our corresponding side lengths. The reason why, not perpendicular, excuse me, parallelism. The reason it's important that these lines are parallel is that it helps to prove the angle part of our definition. If lines are parallel, they do adjust at the same angle, hence you got parallel. Okay, moving on to our last set of examples. Again, I set these up with coordinates. You might want to pause to do that. Try these on your own, obviously, and then come back to check. Maybe we can get away with page width. Okay, maybe. Yeah, this is just a mess. All right, we'll just do it from here. Okay, so the same principles apply though. Is this actually a dilation? Well, the first thing we should check are all the K factors. And so we have -1, -1, -3, -3. And so they are the same numbers, and we have a K factor of -3 over -1, or just equal to 3. Now, likewise, we could just set it up as -1 over -3 and get a K factor of 0.3 repeating. And unlike the previous example, I don't know which one it is because it doesn't give us an indication which one came first. But it's not important that we know which one came first. It matters that we can affirm all the K factors. If we look at the green vertices, we do have 0 over 0, which is uncalculable. We just ignore that. So we have 3 over 1, which is just 3, or we have 1 over 3, which is just 0.3 repeating. Repeating. There we go. Last set, we have -3 over -1, or we have 3 over 1. Okay, so either way, that's going to result in a value of 3. And then if we reverse it, since we're all using the same numbers here, we can also see that we have a value of 0.3 repeating. And so since all the K factors are the same, both directions in this case, we're pretty sure a dilation's happened. To bring us home here, we definitely want to check our dilation lines. And so if we connect, and we connect, and we connect them a little off here, but you get the point. They all come back to a central point, again, 0, 0. Here we have a K factor of 0.5, which means we're just cutting all these values in half. Okay, and so we take 4, 8, and a half. That'll be 2, 4. 1, 2, 3, 4. And because of like the writing is getting kind of weird, I'm not going to put in the vertice value, but we can agree that should be 2, 4. If we take 6, 6, that should be 3, 3. Okay, 4, 4 should be 2, 2. And then 6, 4 should be 3, 2. So 1, 2, 3, 1, 2. Okay. So as I draw in kind of this image, and I know it's not perfect, okay, we should note that all the corresponding lines are parallel, again, indicating same angles. And then if we trace all these lines back, they should hit at a central point, which is probably 0, 0, given our experience. And lo and behold, they indeed do. Okay. Now, are drawing these lines necessary to like the product? No, not necessarily, but they actually do help us out quite a bit to confirm it. All right. So those are your notes. The sub has 3 assignments for you. There are 2 rounds of what I would call like basic mixed practice, and then there's a little bit tougher review / big homework assignment. Assume they're all due on Friday. That's when we'll address them. So that's what I have for you. So best of luck. Right? You guys have a wonderful day. Study hard. Don't give the sub a hard time, please. Come back with a good report. I'd much appreciate that, and so would the school. All right? Have a good day.